Let's talk about metals, nonmetals, and metalloids. First off, metals. Not rocket science here. Metals have a metallic luster. They're shiny. They're malleable, which means you can hammer them into shapes. You can bend them. You can press them into shapes. They're ductile, which means you can pull them into a wire. And they're conductive, which means heat can go through them. Also, electricity can go through them. And they're all solids. So metals, they're metallic. Duh. You can press them into shapes. They're ductile. You can pull them into a wire. They conduct heat and electricity. They're solids. Almost all of them, except for mercury. You see all these gray things here? These are all metals. That's a lot. Most of our periodic chart is metals. Notice even things like calcium, things that make up your bones and your teeth. That's a metal. Sodium, that's a metal too. And then we've got gallium here. That's a metal, but when you put it in your hand, once it warms up a little bit, it'll actually turn into a liquid. I think I've got a video of that coming up. And then there's nonmetals. Nonmetals are the exact opposite of metals. Nonmetals, they're brittle. They break easily. You can't hammer them into shapes. They don't conduct heat and electricity. Some of them are gases. So nonmetals are the exact opposite of metals. And they also don't have luster. They don't reflect light the same way that a metal does. And there's a video about metalloids. It's not terribly important. It just kind of goes through some nonmetals. I don't know why I've labeled that one metalloids. I'll have to fix that. Take a look at all the nonmetals. All the nonmetals are yellow. They're right here on the periodic chart. Helium is a nonmetal, but it belongs in family number 1, so it's kind of a black sheep of the family. But all the yellow ones are nonmetals. Remember, they don't conduct heat and electricity. You cannot hammer them into shapes. They do not have metallic luster, and many of them are gases. Let's talk about metalloids. Some people call them semi-metals or semiconductors. I prefer to call them metalloids. And there's the word metalloids up here. Metalloids are kind of halvesies. They share some characteristics of metals and some characteristics of nonmetals. They're kind of right in between, both physically and ideally, I guess. So they're semiconductors, which means they can conduct heat. So there's a video of semiconductors, and I'll kind of summarize it for you. They take silicon, a silicon wafer. That's what we use in computer chips. When you try and pass electricity through silicon, it doesn't work. It doesn't conduct electricity unless you heat it. So that makes silicon a semiconductor or a semi-metal or a metalloid, because does it conduct electricity? It depends. It can, but that doesn't necessarily mean that it will. Let's keep going. So all the semi-metals or the metalloids, these are the blue ones here. Notice they fit a particular pattern except for aluminum. Aluminum's kind of an outlier that changes. But all the other blue ones here, those are metalloids. They share characteristics of both metals and nonmetals. And I'm pretty sure on your test, I'm going to give you a blank periodic chart. I'm going to ask you, like, hey, if you found an element that had, it conducted electricity, it conducted heat, it was shiny, where on the periodic chart would you find it? And you just have to point towards the left-hand side. Okay, so an element key is basically this. It's the entry on the periodic chart. It tells you everything you need to know about an element. It contains the element name, the symbol, the atomic number, and the mass of the element. So some element keys are very involved, like these ones down here. It tells you not only the weight, but the melting point, the crystal structure, the acidity. You don't need to know all that stuff. These are the keys right here, and I think you're able to read all that stuff. So next, it says some element keys contain much more information, just like I showed you down here. They can contain lots of information. The symbols of elements are sometimes named after a Greek or a Latin name. So like lead. Lead, its symbol is Pb, and its Latin name is plumbum. It was used in plumbing way back in Greek and Roman times, which was a huge mistake because entire societies got lead poisoning by using lead in their plumbing. bad idea. Don't use lead in your plumbing. But its symbol is Pb because it was used in plumbing. Or like gold, its Latin name is Arium, which means shining dawn. It's kind of weird. Element symbols are sometimes named after scientists, like curium, mendelevium, borium, nobelium, lawrencium. All those are named after certain scientists. So we've got polonium here, which is named after Poland, which is Marie Curie's country of origin. Or mendelevium, named after Dmitry Mendeleev. I know someday there's going to be a wagnorium. I'm excited about that. I just don't know when that's going to happen. And then there is curium, which is named after Marie Curie. So this is kind of an intermission right here. If you need to go get a drink of water, use the bathroom, something like that, now's a good time to do that. So here's Grandma with Shiloh, and let's move on. We're almost done. We got 7 or 8 more slides left. So let's talk about the representative elements. Remember, representative elements are the tall families. Families 1, 2, 13, 14, 15, 16, 17, and 18. Family number 1, remember, it's got 1 valence electron on the outside. They're extremely reactive with water, and they're never found by themselves in nature. They have only 1 valence electron in their outer shell, and they give up that valence electron in order to bond with other elements. And as you go down, they have greater reactivity. So lithium, yeah, you drop it in water, it's going to fizzle. Sodium, it's going to catch on fire in water. Potassium, it's going to pop. Rubidium, bad news, you got an explosion. Cesium, a huge explosion. If you want to watch family number 1 react with water, I'll post a link to that video right here. It's the alkali metals video. It's kind of fun and entertaining. So it shows they drop these things in water, and then you get to see what happens. Let's move on to family number 2. Family number 2 is called the alkaline earth metals. That's the name of the family. Notice all of them are going to have 2 valence electrons. You also never find themselves, they're never by themselves in nature. They're very reactive metals, and they readily lose outside electrons in ionic bonding. So they give up their electrons in ionic bonding. Let's keep going. Let's see. Oh, there's a video that goes along with that. Alkaline earth metals. Not terribly exciting. It just kind of tells you a little bit about family number 2. Let's go to the next one, family number 13, and you're probably thinking, what happened to families 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12? Well, remember, those are transition elements. We don't care about those right now. So family number 13, the boron family. Pop quiz, how many valence electrons does boron have? 3, because it's in family 13. So they all have 3 electrons in their outer shell. They don't bond as easily as family number 1 and family number 2, but they will give up some electrons in order to bond. Here's a video of melting gallium. So it's kind of fun. There's a metal spoon. They put the metal spoon in water, and then the metal spoon melts because gallium's melting point is around 86 degrees. Anyway, let's keep going. Here's family number 14, the carbon family. How many valence electrons does it have? 4 valence electrons. And there's a history of lead. Nothing tested in this video for sure. It's just kind of some warnings about lead. And just as a side note, when it comes to lead, consuming lead, not that you ever plan on doing that, but consuming lead does cause brain problems. And some students I have had in the past have had learning disabilities from eating lead-based paint as toddlers. So toys that have lead-based paint in them, a huge no-no, because of the dangers that you can find in lead. Let's talk about the family number 15, the nitrogen family. There's 5 valence electrons in their outer shell. And one notable element there is phosphorus. It comes in a white form and it comes in a red form. The red form is on matches, so whenever you light a match, you're using some red phosphorus there. White phosphorus, you got to keep it in oil because when you expose it to air, it instantly burns. The Geneva Convention, the people that make rules about war, are considering banning white phosphorus because some bombs are made of white phosphorus. They explode in the air and they cover everything below it with white phosphorus, which means it instantly burns. It's a very horrible, horrible weapon. But that's one of the notable elements there. Let's go to family number 16, the oxygen family. They've got 6 valence electrons in their outer shell. I guess there just wasn't much to say about them other than they've got 6 valence electrons in their outer shell. You got oxygen, sulfur, tellurium, stuff like that. Family number 17, these are called the salt formers, the halogen family. They form different kinds of salts like sodium chloride, lithium chloride. There's all sorts of different chlorides, so they form salts. They have 7 valence electrons in their outer shell. They're known as salt formers. And then lastly, family number 18, these are the noble gases. The noble gases have 8 valence electrons in their outer shell, and because they have 8 valence electrons, they don't want any more electrons. They are completely and entirely unreactive. They do not react with anything or any other element. Sorry, I'm back. So, yeah, the noble gases, they have all their valence electrons. They're all filled. So they have what's called an octet. So they do not bond with anything at all. Noble gases can be kind of fun. There's some videos that go along with this. One of them is an actor. He's breathing in some helium, and as he breathes it out, it makes his voice high. Maybe you've breathed helium before. But there's also videos of people who have breathed in argon. It's not terribly dangerous because it's inert. It doesn't react with anything. But instead of making a high voice, it actually lowers your voice. So I'll do my best to link those on this video as well. They're just for fun. And lastly, we need to talk about the lanthanide and the actinide series. There's not a whole lot to say about the lanthanide series, except its elements 59 through 71. They're soft. They can be cut with a knife, and they used to be called rare earth elements, but they're actually not that rare at all. People thought they were rare. Turns out they're really not that rare. So just as a quick reminder, the lanthanides are the top ones right here. It's the actinides that we're going to talk about now. These are the actinide series. Again, there's not a whole lot to say about the actinide series, except that they're all radioactive. Like thorium, protactinium, uranium, those are the only naturally occurring ones. They're the only ones that you can go outside with a shovel, dig in the ground, and actually strike uranium. Or, hey, I found protactinium in the ground. You can actually dig in the ground and find protactinium. All the other elements beyond element 92, so elements 93, 94, 95, 96, 97, and so on, those are all synthetic. They're man-made. They're made in nuclear laboratories. They're made from nuclear reactions and things like that. You cannot dig in the ground and find those. It's impossible for you to dig in the ground and strike Einsteinium. You can't do that. There is no Einsteinium in the Earth. It's not there. It's synthetic. So the synthetic elements are made in laboratories. One that is notable is americium. It's actually in smoke detectors. Chances are you have americium in your home. It's a synthetic element, and as it goes through radioactive decay, it helps you detect smoke. It's just side knowledge. I know this was a lot to go through. We went through a lot of information. Thanks for being patient. Have a great day.